Hello. Hello, everyone. Okay. Oh. Hi, Ashley. Okay. Let's see. Nope, that worked. Oh, crap. Is that? Okay. Okay. First, does anybody have any questions? Any questions about anything that they would like me to go over in particular? Can everybody hear me? Okay, good, good, good. Okay. Okay, so no one has any questions in particular that they would, any topics that they want to go over? Okay, well, in this exam that we have tomorrow, it is going to be covering all of 1211 and 1212. So it's a fairly large amount of material to cover. So get out my book. What did I do with my book? Lost my book. 1 second, sorry. Oops, there it is. Okay, so it's like I said, a pretty large amount of material to be covering. So, of course, the most efficient thing to do is to kind of cover just the things that you have forgotten. Make sure you kind of reevaluate everything. But I'm going to kind of go over some of the things that I would expect to potentially see on this. I did not make this exam, so I'm not entirely sure. And I have not myself taken this exam. I took the last version of the ACS that we had, but this one is a newer version. So, okay. Just like I said, gonna kind of do an outline of things, give brief descriptions or explanations of things, some things to remember or look out for. What you have to remember with this exam, it's not, none of the problems are meant to take insanely long periods of time. So there's not going to be any intense math like we see in take homes, for instance. There is going to be a good amount of concepts in here. And always remember that it's a multiple choice standardized exam. So I don't know why, but the whole idea is to kind of get you to choose the wrong answer for some, again, unknown reason. So keep in mind that if you've got kind of a wrong misconception, or if you've got a misconception, I guess, there's probably an answer that you're going to get led towards if it's a common one. So try and keep those things in mind when you're doing this. Question all of the answers that you get. Like, okay, does that make sense? If it doesn't make sense, make sure to, go through and try your best to look through every problem. You can be pretty decent about, you can do a lot of rounding with this. Again, because your answers are going to be in a multi-choice format. So when you have to do any math, you can usually use like rounded values from the periodic table to kind of save yourself time. But again, you should have enough time to go back and kind of check your answers. You are given the entire 2 hours. So try and, if you have a chance, go back and check and just make sure every answer seems logical. Okay, so this exam is going to cover chapters 1 through 17. Then it'll be 19 through 21. So all of these chapters are possible to end up on this exam. And this is in the book itself, not from the regular Brown and LeMay book. Some things that people may not have covered is nuclear chemistry. So that is sometimes shown in a 1211 class, sometimes not. Nuclear chemistry is chapter 21. It does not include environmental chemistry, which was chapter 18, the one that I skipped. I will do a little just kind of brief overview of balancing nuclear reactions at the very end of this. If you've not done any balancing of nuclear reactions, maybe look over it a little bit more. But okay, so within chapter 1, or in the beginning part, we talk about matter and matter properties. So some ways that we classify matter. Is as a pure substance. So here we're talking about either a element or a compound, where an element can be atomic in nature, like carbon, or it can be molecular in nature, such as H2. And then our compounds can be ionic, such as NaCl, or covalent, such as water. Okay. So those are the ways we can classify pure substances. And then we also have mixtures, where mixtures are going to include homogeneous mixtures. So colloids and solutions. And then heterogeneous are suspensions. All of these mixtures, what will determine which one it is going to be the particle size within there. Solutions are going to be the most evenly distributed. Excuse me. So they're going to be the one that is going to be smallest particle size. And then after that is colloids, and then suspensions. Okay. After we look at that, we can look at a property. So our properties. We looked at chemical versus physical properties. A chemical property is one observed during a chemical change. And then a physical property is essentially all the rest of them. So ones that you could just observe without changing your substance. So observed with no chemical change. So those are two ways we can represent properties. We can also represent properties as intrinsic or extrinsic. So if we're talking about intrinsic, that's kind of internal. So it's a chemical identifier. And then extrinsic, external. So this is based on amount. Okay. Another way we classify matter beyond its properties or its composition, we can also classify matter by its state. So solid, liquid, gas. I'm not really going to go into those. Those are probably everybody knows, and it'd be just a waste of everybody's time. But you should know within your state, you should know relative energies, densities, and then how volume and shape are affected by the specific state they're talking about. And again, if there's anything, there's gonna be some things that we go pretty quickly through during this review because we don't have a whole bunch of time. But if there's anything you guys need me to stop and spend more time on, please let me know. And if you don't want everybody to know that you're doing that, you can send a message directly to me. Okay, so we've got our states, and that kind of defines our way of classifying matter. Okay, we also have, when we're talking about matter, there are lots and lots of laws that we look at. Law of constant composition, law of definite proportions, law of conservation of matter. So those are going to be pretty easy to figure out. So I'm going to kind of go past those as well. But maybe if you don't remember the different laws of matter, review those. So constant composition, definite proportions, and conservation of matter. Okay. We also look at energy. At the beginning, we kind of look at it as just a very general description where we're talking about kinetic, our motion energy, versus potential, our stored energy. And then we could look at work versus heat. So work, our energy to move an object, heat, our heat or our transfer of energy to cause a temperature to change, the temperature of an object to change. And that's all we really talk about at the beginning. But with kinetic energy, that energy is equal to 1/2 mass times velocity squared. So the more massive something is, the faster you're moving it, the more kinetic energy it has. So that's one of the things they look at. They also look at work, which is force times by distance, where force is mass times by acceleration. So more massive, the faster you're moving it, the further you're moving it, the more work. So those are the energies. These are the ones we focus on most within chemistry, because we're looking at electrostatic potential energy. We're looking at potential energy within bonds. We're looking at heat transfer from one substance to another. So those are really kind of the ones we focus the most on, and I'll hit back on those when we get into that portion of the review. Okay, units. You should know your metric units. right? So make sure you review those if you do not remember them. You should also know your SI bases, base units. So most of them are going to be things we'd expect, where like length is meters, temperature is Kelvin, time is seconds, amount of substance is moles. Then there's mass, which is kind of the weird one, because mass is going to be in kilograms, right? So that's one of the ones that is a weird one. We also have electrical current and luminosity, or luminous intensity, but we don't look at either of those in chemistry, so we're going to ignore those as well. But the base unit that's weird is that mass. And then we also have, within SI units, we have derived SI units, which is where we take 2 or more SI units and multiply them together. For instance, if we had density, density is mass over volume. So the SI unit for density would be kilograms over liters, right? I guess just as a note, the SI unit, we use degrees Celsius so much in chemistry, but the SI unit is Kelvin. You should be able to do temperature conversions, especially going from Kelvin to Celsius and vice versa. Right, so you should be able to do this conversion without any issues. Going from Fahrenheit and converting between Fahrenheit and Celsius is a little bit more complicated. And I don't think you're given this equation, but if you can remember, the 0 degrees Celsius is 32 degrees Fahrenheit, and 100 degrees Celsius is 212 degrees Fahrenheit. You should be able to figure that out, hopefully. And this is just looking at your freezing point and your boiling point of water. So those are usually ones that people memorize pretty easily. So just as a note, if you can't remember the equations, which I rarely ever do, so it'd be completely understandable if you do not. These are 2 good benchmarks to use to try and remember what the other temperatures are. You can essentially just kind of from there get an idea at least of what would be a reasonable value. And again, it's a multiple choice, so a reasonable value would be helpful. As a note, density, even though that's the SI unit, we usually give it in grams per centimeters cubed for a solid, or grams per milliliter if it is a liquid. Oh, we also have energy. So we have a derived SI unit of energy. This is going to be kilograms times by meters squared over seconds squared. So this is going to be our mass unit, our length unit, and our time unit. And this is equivalent to joules. So if you're ever wondering why kilograms are in there, it's because we're using it. So joules is an SI unit. Dimensional analysis. You should know how to do dimensional analysis. If anybody needs some practice problems on dimensional analysis, let me know. This I'm not going to go over hardly at all. Just keep in mind that with dimensional analysis, you're using conversion factors. And these conversion factors are being treated like 1. The reason we treat it like 1 is because we have 2 things that are equivalent to each other. For instance, 1 liter is equal to 1,000 milliliters. Because these are equivalent, if we divide it out, 1 liter, oops, try that again. 1 liter divided by 1,000 milliliters, that is equivalent to 1, right? Which is why we can do whatever we want with these unit conversions. We can divide by them, we can multiply them, we can multiply them several times. It doesn't really matter because the unit conversions themselves, it's just like multiplying or dividing by 1. It doesn't affect the actual value. Okay, that's chapter 1 in a nutshell. Any questions? Okay, we're trying to go a little faster because that took far longer than I expected. Okay, next we look at the atomic structure. It is really good if you review the specific experiments and scientists that led up to the discovery of the electron and proton and nucleus. So specifically, you're going to be looking at J.J. Thomson, who used cathode rays to determine that there were negative particles that can be ejected from an atom, and he came up with the plum pudding model. And then you have Robert Millikan, who did the oil drop experiment, and from that and J.J. Thomson's experiments, he was able to determine the mass of an electron. And then you have Rutherford. What's Rutherford's first name? Rutherford. I have to look. Rutherford. Ernest, maybe? Ernest? I think it's Ernest. Yep, Ernest Rutherford. Ernest Rutherford. He's the one who did the gold foil experiment. The gold foil experiment, because of the way it was set up, as you shot these alpha particles at this very thin gold foil, most of it was not deflected. It was something like 1 in 20,000 or something like that that was deflected, which led to the discovery, it led to disproving the plum pudding model, and it led to the discovery that the nucleus is very, very small. It holds all of the mass of the atom, and it has a positive charge. So through their experiments and some others, they found that protons and neutrons are in the nucleus, electrons are orbiting the nucleus, and protons and electrons have the same charge magnitude, just different signs. Protons +1, electrons -1, and that protons and neutrons are very massive, while electrons are very non-massive. You should also review atomic number. So number of protons. Mass number. Protons plus neutrons. And this is the actual number. That's not what we find in our periodic table. Our periodic table has the average atomic mass, taking into account isotopes and relative abundance. So you should definitely know the difference between those. And then you should be able to calculate the charge based on the number of protons minus the number of electrons. You should also be able to predict charge based on the periodic table. And you should be able to calculate these, the average atomic masses. Again, if there's any questions about how to do any of this stuff, please stop me. You should understand how the periodic table is arranged. So if you think about a table, we know that we have periods. So those are going to be our rows. We have groups. Those are going to be our columns. And groups, these elements have similar chemical properties. And you should know why. It's because they have the same number of valence electrons. Right? Our periods, that tells us what our N value is. So thinking back to chapter 6, but we'll hit on that in just a minute. You should know the metals are on the left side of the periodic table. The non-metals are on the right side of the periodic table. And our metalloids are on that stair step. You should know that metals are malleable, ductile, electrically and thermally conductive, generally high melting. Non-metals are the exact opposite, brittle and low melting and all that. And then metalloids are somewhere in between. You should know the difference between a compound and a molecule. Compound, you have to have different elements in it. Molecule, you have to have 2 or more of any type of non-metal. And then an atom is monoatomic. You should be able to solve for empirical formulas. And you should be able to do this using a variety of different techniques, including you should be able to use percentages of each element, keeping in mind that you could just take everything out of 100 grams. And then you should be able to do combustion analysis. So make sure you're able to do combustion analysis. Make sure you can have percentages of elements and take either one of these to solve for your empirical formula. Also, if you have the formula mass, not formula mass, molar mass of a Icania. Give me just 1 second. If you have molar mass of a substance, you should be able to determine the molecular formula if you are given or determined the empirical formula. Okay, combustion analysis, we can do that, absolutely. Let me find an example, because I can't come up with one off the top of my head. Sorry about that. Okay, so let's say we have a compound that contains, this is combustion. We have a compound that contains hydrogen, carbon, and oxygen. So it's a hydrocarbon with an alcohol. And when it's combusted, so let's say we have 0.255 grams of the sample, and we combust it. And when we combust it, we get 0.561 grams of CO2, and then 0.306 grams of H2O. Generally, that's what you're going to see is you're going to be given a mass of carbon dioxide, a mass of water, and a massive sample. I don't think they're going to do anything super crazy with these, so that should be plenty. You're going to go take your grams of carbon dioxide. Your goal is to get to moles of carbon, and here your goal is to get to moles of hydrogen. And then once you have that, you can get to mass of carbon, mass of hydrogen, And these two values can be subtracted from your sample mass. And you can get your mass of oxygen and then moles of oxygen. And once you have moles of each of your substances, you can get your empirical formula. Okay, so we have 0.561 grams of CO2. It has a mass of 44 grams per mole. Dividing that out, we get well, they didn't do the calculation here. I guess I need to get out of the calculator. Actually, let's do this a little bit more quickly. Let me just write things out completely. This is moles of carbon dioxide. And once we have moles of carbon dioxide, we can say, okay, for every 1 mole of carbon dioxide, we have 1 mole of carbon, right? So let's get into carbon. So we have 0.561 divided by 44. This gives us 0.01275 moles of carbon. And then we do still need to get this into grams. So for every 1 mole of carbon, we have 12.011 grams. We're going to take what's on the periodic table. And this gives us 0.153 grams of carbon. Do the same thing with our water. So we have 0.306 grams of H2O. 1 mole of H2O has a mass of 18 grams. Again, I'm just kind of rounding things to make it a little bit more simple. And then for every 1 mole of H2O, it's H2O, we have 2 moles of hydrogen. So taking our 0.306 divided by 18 times by 2 gives us 0.0340 moles of hydrogen. And then 1.008 grams, and I guess I just do 1. I don't know why I did it like that. That's good. 1 mole of hydrogen gives us 0.0343 grams of hydrogen. We can then take our sample mass, 0.255 grams, subtract out our mass of carbon and our mass of hydrogen. The reason that we need to do this to solve for our mass of our oxygen is because combustion is CXHY plus O2 goes to CO2 plus H2O. And let's say we have OZ. Not all of the oxygen is coming from our sample. A lot of it is coming from the O2 that's being added in for the combustion reaction. So we can't do what we did for carbon and hydrogen because all the carbon and carbon dioxide is coming from our sample. All the hydrogen in the water is coming from our sample, but not all the oxygen is coming from our sample. So we'll take our 0.255 grams of sample, subtract 0.153 grams of carbon and 0.0343 grams of hydrogen. And this gives us 0.0677 grams. And this would be of oxygen. So we'll take 1 mole of oxygen is 16 grams, giving us 0.00423 moles of oxygen. And then we take all of our mole amounts and divide by the smallest number, which is the oxygen. So we'll divide by 0.00423, 0.00423, and 0.00423. That gives us a 1 there. That gives us a 8 here. And a 3 here. So our substance is C3H8O. Any questions about that? Okay, I'm gonna keep going then. This is getting recorded, so it'll go back up. So if it's a little confusing initially, either let me know or watch it one more time to see if it makes more sense. Okay, you should be able to name. You should be able to name compounds. I don't know if you need to worry about organic naming. I wouldn't worry too much about organic naming, but you should be able to name inorganic compounds and either ionic or covalent. So name compounds, so ionic compounds, binary covalent compounds, and you should be able to name acids. So if you have not already done so, review your polyatomics, right? Make sure you know how to name all of these things. It's going to be assumed throughout the entire test that you know how to name and that you know how to go from name to formula and formula to name. So there might not be any specific questions on it, but you might lose points because you don't know, you might get a question wrong because you don't know what they're talking about because you don't remember your naming. So make sure you review your naming. Okay. You should be able to balance equations. The biggest thing to remember with balancing equations is keep polyatomics together if they are they're on both sides of the equation. Let's see. You should also be able to recognize the different types of reactions. So we've got decomposition. That's when something is decomposing. So we have A going to B plus C. Combination, we're combining components, right? A plus B goes to C. Combustion, we are combusting something using water. So it's usually a hydrocarbon with oxygen going to carbon dioxide plus water. However, as a note, H2 plus O2 going to H2O is still considered a combustion reaction because we are combusting hydrogen in this particular case. So we don't necessarily have to have carbon, but usually we do. Acid base, neutralization. We have done so much of this. So if you don't know how to do this, it'll be very sad. But we have an acid plus a base going to water. We can have different kinds of bases. We can have a nitrogen base. We can have a carbonate base. We can have a bicarbonate base. With nitrogen bases, you're going to have one product, usually Lewis addict, right? We also have sulfur bases. With these, we're going to have a gas product. So either carbon dioxide or H2S gas. Let's see. Oh, and of course there's the hydroxide base, which is the one that we are most familiar with. Redox reactions. Again, this is something we have gone over several times. So we should hopefully know that. And precipitation reactions. With a precipitation reactions, we will have a solid solute, or solid, not solid, solid product. But everything else should be aqueous. Sometimes we have two substances coming together to produce two solids, but that's much less rare, or that's much more rare. And then we have a couple more general. We have single replacement. And a lot of redox reactions are these. Not all of them, but a lot of them. That's going to be A plus BC going to AC plus B. And then double replacement. A lot of precipitation reactions are these. We also call them metathesis reactions. This is where we switch partners. AB plus CD goes to AD plus CB. Keep in mind, a lot of these are ionic, so you will need to kind of balance charges with those. Let's see. I mean, Avogadro's number, elemental composition, those are things you should know how to do. You should be able to determine molar mass. You should be able to convert between masses and numbers of particles. All of those things should be. Yes, that's a very good point. I hadn't gotten to that chapter yet, but you will have to predict product. So for a lot of these, you will have to predict product. And also go ahead and put that out. So if we are predicting product, that means we're given our reactants and we need to figure out what our products are. That's going to include things like simple redox reactions, including predicting if a reaction will occur based on redox potentials or reduction potentials. And then acid-base neutralization reactions, absolutely. Neutralization reactions. So you'll definitely have to predict product there. Precipitation reactions. If you do not remember your solubility rules, revisit those. Usually you can kind of focus on just the ones that are soluble and then the crazy exceptions. And then look a little bit into the ones that are always insoluble. So think about always soluble. We have substances with nitrate, ammonium, alkali metal ions, and acetate. I guess that's acetic acid, isn't it? So anything that's going to form with these are going to be always soluble. And then we have things that are going to be usually soluble. Those are going to be things like sulfate and halogens, unless they are with something that is less likely to be soluble. So we have our always insoluble with these exceptions. So those are going to include things like, one second. I completely passed it over. Sorry, 1 second. Sulfides, carbonates. I guess I should also put H+ in here, because if we have acids of these are going to be soluble as well. Phosphates and hydroxides. These are always insoluble with the exceptions of the always soluble. And these two are also soluble when we soluble with Ca2+. SR2 plus and Ba2 plus, right? And then our sometimes soluble, that's going to include sulfates and halogens. And that's going to be with the exception of, generally the exceptions are going to include silver, mercury 1, which is Hg2 plus, which a lot of people forget that that's mercury 1. Lead, actually, the sulfates specifically are also going to be strontium, is insoluble, and barium. So it gets a little confusing at times. And really, silver is only for halogens. Okay. Let's make sure I hit all the topics from that. That kind of went. You should be able to do stoichiometry. Again, that's a thing that is kind of expected, so I'm not really going to go into that. But you should be able to do limiting reagent problems. You should be able to do percent yield, percent error. Keeping in mind that percent yield plus percent error should equal 100%. So those should be things you should know how to do. Again, if those are things that you're not entirely sure about, send me a message and I will send you some practice problems. You should know what an electrolyte is. You should know what specifically a weak one is, a strong one is, and a non-electrolyte. So you should be able to recognize something as a weak electrolyte, a strong electrolyte, or a non-electrolyte. And you should understand what type of soluble compounds you're going to have if you have a weak electrolyte versus a strong electrolyte versus a non-electrolyte. Keep in mind that both of these are going to have dissociation, but the amount of dissociation, less dissociation, weak, more dissociation, strong, or all dissociation, strong. You should be able to write out, or you should be able to, I guess you would really have to write out, but you should be able to recognize net and complete ionic equations. And you should be able to recognize spectator ions. So make sure you know all of that. Let's see. You should know what an acid is. You should know what a base is. You should know what a neutralization reaction is. You should know all the components of a redox reaction. So with our redox reactions, you should be able to recognize what's being oxidized, what's being reduced, what is the oxidizing agent, what is the reducing agent. You should be able to balance these in acid and base and determine how many electrons are going to go. You should also be able to determine if a redox reaction is written in the spontaneous direction or the non-spontaneous direction. You should definitely be able to solve for oxidation numbers. All right, we've gone over a lot of these things this semester, which is really nice. Any of those will always be the react. Yes, all of these are reactants. Great question. Absolutely. So yeah, the substance that's being oxidized, the substance that's being reduced, the oxidizing agent and the reducing agent are all going to be reactants. You will not find any of that on the product side. You should be able to do concentration calculations. And for a full list, we have molarity, molality, parts per, mole fraction, mass percent, volume percent, and dilution. M1V1 equals M2V2. As I note, the dilution calculation can be done with just about any unit. It doesn't necessarily have to be molarity. But you should be able to convert between units. You should be able to use concentrations in solution stoichiometry, those type of things. You should also recognize the components of a titration. All this stuff we've recently gone over, it's all stuff we went over in 1211, right? So you should know what a standard solution is. So our thing that we know the concentration of, right? You should know what the equivalence point is. I think a few people need to review that. Half equivalence, if we're talking about a weak acid or weak base, right? You should know what an indicator is. You should know what a titration curve will look like. So make sure you're able to recognize a titration curve. Be able to do titration calculations for strong or weak acids, or say for strong or weak acids or bases. You should know what the titrant is and what the analyte is. So these are all things you should know within a within titration. So be able to recognize if you have an acid titration or a base titration, and what could be the analyte or the titrant. Be able to recognize if you're dealing with a weak acid versus a strong acid, a weak base versus a strong base, a diprotic acid, a triprotic acid. If you have a diprotic acid, keep in mind it'll have 2 equivalence points. If you have a triprotic acid, it'll have 3 equivalence points. So those types of things. We get into energy after that. With energy, you should be able to relate work and heat, right? You should know the first law. So you should know your laws of thermodynamics. They go from 0 to 3, or the ones we look at. Yeah, the ones we look at in here, in 1211 and 1212. So this is including 1212 as well. So anything that relates to 1212, I'm also going over within what I'm talking about, by the way. You should understand how the sign of energy works. Whether it's, no matter what type of energy it is, whether it's internal energy, which is our E, enthalpy, which is our H, entropy, which is our S, Gibbs free energy, our G, should understand what a positive or a negative value means in each one of those cases. So for internal energy, enthalpy, and Gibbs free energy, if you have a negative, or work or heat, if you have a negative, that means that the energy is coming from that substance. So it's leaving, it's exiting. And then if it is positive, if it's positive, then it's going to be entering, it's endo. So keep in mind that you should know the difference between a state function versus path function. And you should be able to give examples of each. Right? With a state function, we only care about the initial and final states. A path function, we actually do have to care about the path that our substance takes. So work and heat are considered path functions. Internal energy, enthalpy, Gibbs free energy, entropy, temperature, volume, pressure. Those are all considered state functions because we only care about the initial and the final. You should be able to solve for enthalpy. We have like 5 billion different ways that we solve for enthalpy. So just as a note, within enthalpy, within energy in general, if we're talking about a reaction, we only care about the work that is due to the expansion of a gas. So when a gas expands, when a gas is formed during a reaction, it's going to expand, and then work is done by the system. If a gas is consumed during a reaction, then usually the gas will be compressed and work is done on the system. On the system is endo positive, by the system is exo negative. So that's really the only work we care about within this class, is because it's chemical reactions. So we think about the expansion or compression of a gas. So we call that pressure volume work. And that's a component of enthalpy. When we think about enthalpy, it is delta E plus P delta V. So that is that pressure volume work right there. So this is at a constant pressure. So our gases have to have the ability to expand or compress so that we can keep a constant pressure. And if we have a constant pressure, our delta H is equal to our heat, because we don't have to worry about work. Work has been removed from that equation. If we have constant volume, then our heat is related to our internal energy. So we see this with calorimetry, specifically constant pressure calorimetry. And then we see this with constant volume calorimetry. So this would be bomb calorimetry. And then this would be coffee cup. Noting that, you should be able to remember your MCAT, right? Your heat is equal to your mass times by your specific heat times by your change in temperature. And you should understand, again, what negatives and positives mean in there. You should be able to solve for any energy using the idea of final minus initial, or products minus reactants. So you can use that for delta H, for delta G, delta E, and S. So you can use the idea of products minus reactants for any one of these to solve for them, if you're given that information. You should understand what the specific heat means. The idea that if you have a large specific heat, it's something that holds on to heat or takes a lot of energy to heat. A small value means that it's easy to heat and does not hold on to heat, so it's very good at conducting heat. We have done these so many times that you should not need any review on what Hess's law is. But Hess's law takes advantage of the fact that enthalpy is a state function. But you should be able to do Hess's law whether we're talking about adding equations or using formations. So adding equations or using formation values. You should also be able to solve for bond enthalpies. This is always a little not hard, but with bond enthalpies, you must draw the most stable Lewis structure. You cannot, and they will give you a reaction. If there's a bond enthalpy problem, they will give you a reaction where if you did not write out your Lewis structures, you would have the wrong bonds. So make sure you draw out your Lewis structures with that. And with this one, we don't usually think about it as much of a product versus reactant. Just know that bond breaking requires energy. So that's going to be a delta H that is positive, and then bond making releases energy. So your delta H here is going to be negative. Okay, so keep that in mind if you get to a bond enthalpy problem. Essentially, all of the bonds on your reactant side will be given positive values. All the bonds on your product side will be given negative values. So you don't think about that as a products minus reactants. All of your bond enthalpies will be given as positive values. But when you're solving for it, make sure that your reactant side, all those values are positive. Your product side, all of them are negative. I think that's it for this, the main components of that. Oh, electronic structure of the atom. So this is something that gives people a lot of trouble in 1211, and it's something we don't review that much in 1212. So try very hard if you have a chance to review your electronic structure. So looking at light as a wave and particle. So some of the equations that you're going to be using, E equals H nu, C equals lambda nu. So those are really the two big ones. You can combine them and get E equals HC over lambda, right? You can use any one of these equations for light. But keep in mind, you can only use it for light because that is the speed of light. If you're not going at the speed of light, you have to use a different equation, specifically a matter wave equation. You should know the experiments that led up to, or observations, I guess I should say. Observations that led up to thinking of energy as quantized, and eventually led up to the idea of quantum mechanics. Okay, so this is going to include black body radiation. It's going to include the photoelectric effect. It's going to include our line spectra. So these are the three experiments that led up to the idea that energy is quantized, and it led up to Bohr's atomic model. Right? So his model of the atom and the nuclear atom. And then it also led up to a couple other things, including the idea that light acts like a particle. And then from all of this, we start to get a couple of additional things like matter waves. Oh, and you should, for atomic model, you should know the postulates, and then which ones have been disproven. So the idea of things being in orbits, actually orbiting the nucleus has been revoked, right? That idea. But the big thing that we get from our Bohr model is our principal quantum number n. Okay, so make sure that you review Bohr atomic model. We have our matter waves, which also came about. So the idea that if light acts as a particle, then particles must act like waves. So that the matter wave takes into account if you have something that is not moving at the speed of light, because it has a mass and a velocity there, right? So this is mass, and this is velocity, not this, which is frequency. Okay. Again, if anybody has a question, please stop me. Then we have Heisenberg's uncertainty principle. With the uncertainty principle, it's essentially if we treat an electron like a wave, then we can't really precisely know its location because it's extending out into space. And a wave extended out into space does not have a precise location. So since we don't have a precise location, when we know what the energy of the wave is, or if we know the location, then we can't know the precise energy. We have uncertainty in the position. And the uncertainty is small. It's a very small value. But for an electron within an atom, the uncertainty is greater than the size of the atom. And all of these, every one of these things led up to the idea of the quantum mechanic model. So this is where we have Schrodinger treating a electron like a plucked string. And from this plucked string idea, that the wave, that particle in a box, so particle in box, the electron as a wave. He was able to form these mathematical functions. They're called psi, right? Those are the wave functions that the wave functions that were developed through solving for Schrodinger's equations. This is the product of Schrodinger's equation. And then within here, we then can take, this is a sinusoidal, a sine wave function. By squaring that sine wave, we can get the electron density map or electron probability in 3 dimensions, right? So this is where we get our s orbitals and our p orbitals and our d orbitals and our f orbitals. This is also where we get, so Schrodinger's equations, we get our orbital shapes. And in addition to that, we also get our quantum numbers. And I feel like most people probably have taken quantum numbers and shoved it out of their brain at this point. So I'm going to do just a real small little, this is what quantum numbers are. We have n, which is our principal quantum number. This is going to be the same as a period number. And this will tell us our shell or our energy level. Then we have L, our angular momentum quantum number. And this is going to tell us the shape of the orbitals in the subshell, which that subshell is L. N is any integer value. It does not equal 0. L is going to be any integer value between 0 and n minus 1. Then we have our m sub L. This is our magnetic quantum number. This is going to talk about, this is going to be the orientation of a specific orbital in the subshell L, and it has values between negative L and positive L. And then this is our energy level. These two together, that's our subshell. These three, that's our orbital. And then to describe an electron, we must bring in the idea of our spin magnetic quantum number. Which has values of positive 1/2 or negative 1/2, where positive 1/2 is spin up, negative 1/2 is spin down. So if you wanted to describe an energy level, you're just talking about your N. If you want to talk about a subshell, you're talking about your N and L. If you want to talk about orbital, you have to talk about M, L, and M sub L. And then if you want to talk about a specific electron, you talk about all 4 of your quantum numbers. You should know what a node is and how to calculate a node. Number of nodes, I guess to say. So with nodes, we have radial nodes or angular nodes. So when we think about our radial nodes, that's based on what energy level it's in. And then our angular nodes are the ones that are based on what our L value is. So make sure you know your radial and angular nodes. You should also be able to calculate number of electrons based on quantum numbers. Sorry, I'm getting really lazy about writing. Okay. Everything's still working, right? I haven't seen my screen in a while. Okay, yeah, okay. Any questions so far? Okay, keeping on then. You should be able to do, oh, yeah, so electron configurations. And orbital diagrams. More than likely, you'll be given an electron configuration or an orbital diagram, and be asked to tell if it's valid or invalid. So when you're thinking about electron configurations, you really just have to think about, the maximum number of electrons that can go into a subshell. And then you also have to think about your Aufbau principle, because that's going to tell you the ordering of the subshells energetically. So keep in mind it goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, yeah, so on and so forth. So make sure you know your off-bar principle. With orbital diagrams, you also have to keep in mind Hund's rule. So the idea that you want to maximize spin, so you're putting things in singly and putting them in spin up first. This is why we have abnormal electron configurations, such as things in group 6 and group 11. So stuff like chromium and copper have abnormal electron configurations because of Hund's rule. And then Pauli exclusion principle. The idea that we're going to have each electron in an atom having its own set of 4 quantum numbers. So this brings us to the idea that when you do pair up electrons, the second electron is going to go in the opposite spin as the first one. You should also be able to do you should be able to do condensed electron configurations. And you should be able to do electron configurations for ions. With ions, make sure you remove electrons from highest N values first. It's really by highest N and L value. So if you would, for instance, remove 4s before 3d, or 4p before 4s or 3d. Okay, that's everything there. Periodic trends. So you should know your trends, know all trends. The trends, the one that you should focus on the most is effective nuclear charge. And maybe look at Slater's rules. You know, calculating out the effective nuclear charge. Make sure you're able to do that. Understand how effective nuclear charge works and the trend there. From there, you should be able to come up with all the rest of the trends. But the other trends that you will need to know: atomic radius. You should also understand ionic radius based on effective nuclear charge, and number of electrons and electron-electron repulsions. So atomic radius, you should know your first ionization energy. Your first ionization energy trend. And you should know when you're going to have jumps in ionization energy. Specifically, when you're going to remove a core electron. Right? And know that each subsequent electron that you remove is going to require more energy than the electron before it. So you need that. You should know where, and you should also know the definition of ionization energy. This is from from a gaseous atom or ion. Right, gaseous. So this is not the same as the work function. So the work function is removing an electron from just an atom. With ionization energy, we're looking at removing it from a gaseous atom or ion. Electron affinity. Why is it called an affinity? Right. So you should understand trends in this. So there are general trends. This is not the best trend, but there are some that are abnormal, and those are usually the ones you're going to want to look at. And the same idea here, this is adding an electron to a gaseous atom or ion. Electronegativity. I don't think you're going to be given electronegativity values. So just note that most things in the right part of the periodic table, when you bond it to something that's right next to it, so oxygen, nitrogen, oxygen to fluorine, oxygen to sulfur, nitrogen to oxygen, nitrogen to carbon, nitrogen to phosphorus. When you bond something that's right next to it, more than likely that's going to make a polar bond. You usually have to go 1 down and 2 over to get to the same electronegativity. So carbon and sulfur have the same electronegativity values. Nitrogen and chlorine are pretty close as well. And then a carbon-hydrogen bond is the last bond that is non-polar. Anything that has a greater electronegativity difference than a carbon-hydrogen bond, or the difference between carbon and hydrogen, is going to be considered polar. All the bonds that have less will be non-polar. You should also understand about metallic character. We have our metallic character, which is going to be looking at things that are more metallic in nature versus non-metallic in nature. If something's metallic in nature, it's going to have low ionization energies. It's going to have non-negative electron affinities. It's going to have low electronegativity values. It's going to be malleable. It's going to be ductile, those type of things. And then you should kind of just understand what's going on. Noble gases are very non-reactive. Alkali metals are incredibly reactive with very low ionization energies. Alkaline earth metals are reasonably reactive, but less than our alkali metals. And then our halogens, which halogen means salt forming, they really like to react with metals to form salts, which are products of neutralization reactions. Okay, Lewis structures. You should be able to draw Lewis structures. Make sure they're valid. So specifically most stable. You should be able to, you should know what the octet rule is. You should know what violates it or what is able to violate it. So things in period 3 and below, or things that are really small like hydrogen or helium. You should be able to calculate formal charge. So keeping in mind formal charge is equal to number of valence electrons minus number of dots minus number of lines. I recently saw this. I usually think about it as number of lone or non-bonding electrons and number of bonds, but I like it. You can subtract out the number of dots and the number of lines on your structure. You should be able to, so another trend is lattice energy. You should know what lattice energy is and what the trend of lattice energy is. So if we have larger ions, they're going to be further apart. So the lattice energy is going to be less. If we have greater charges, then they're going to be closer, or they're going to be, they're going to have a greater electrostatic interaction. So the lattice energy is going to increase. So this is going to follow along with the electrostatic potential energy. The idea that the greater the charge, the smaller the distance, the greater that electrostatic potential energy. greater electrostatic potential energy is going to lead to larger lattice energies. You should also know the definition of lattice energy. So thinking about the energy required to take a solid substance, solid ionic compound, and break it down into gaseous ions. So usually lattice energy is given as a positive value because it requires energy. You should be able to determine if a bond is polar or nonpolar. And we're going to be doing VSEPR. There's definitely going to be VSEPR on this test. Absolutely going to be VSEPR on this test. So make sure you review VSEPR. So you should know your different geometries, both electron domain geometries and molecular geometries. And you should be able to determine if a molecule is polar or nonpolar based on bond polarity and molecular geometry. Again, if this is something you guys need any additional practice with, let me know. You should also be able to draw bond dipoles. I already talked about formal charge, right? Calculating that, yeah. Okay. Resonance. You should be able to draw resonance structures and determine if a structure has resonance or not. And keep in mind, if you have resonance structures, that is going to be energetically favorable, that stabilizes the molecule. We already talked about VSEPR. You should definitely understand VSEPR. And within VSEPR, you should know your bond angles, your geometries, both electron domain and molecular. You should understand the effect of non-bonding electrons and multiple bonds on bond angles. So keeping in mind, if you have lone pairs, they repel more than any of the other type of bonds or any of the bonds. So they're going to usually make bond angles smaller. Triple bond repels more than a double bond, so that will also, although that's not really going to be much of an issue here. And then double bonds are going to repel more than single bonds. So yeah. Additionally, from VSEPR, you should know hybridization. So we use the hybridization model to describe our geometries that we see in VSEPR. So you should be able to determine the hybridization of an atom within a molecule, whether it is a single central atom or a multiple central atom, based on how many bonding orbitals it has. So again, based on our, well, it'd be based on our electron domain geometries. So hybridization is based on electron domain geometries. You can determine your number. If you know your number of electron domains, you can then determine your number of hybrid orbitals. And once you know your number of hybrid orbitals, you can determine your hybridization. Keep in mind, you have the availability to have one S, up to 3 Ps, and 2 Ds, depending on how many you need. You should also understand that if you have, if you have multiple bonds, so double or triple bonds, you have unhybridized p orbitals. And these are going to be parallel to each other, right? That makes our double bond. That is a pi bond. That's in comparison to a sigma bond, where you have direct overlap. Review MO theory. There's probably not a lot on MO theory because it's kind of a hard one to do multiple choice, but you should be able to come up with bond order from an MO diagram. You should be able to come up with your HOMO and your LUMO. So highest occupied molecular orbital, lowest unoccupied molecular orbital. And you should be able to recognize bonding versus anti-bonding molecular orbitals. So you should be able to recognize those. Keeping in mind anti-bonding is not good, bonding is good. And with this, we can determine our bond order. I think that's a big things with there. Oh, you should know the difference between diamagnetism, the idea that you don't have any unpaired electrons, versus our paramagnetism. The idea that we have at least one unpaired electron, which leads to slight magnetism within a material. And you should know the difference in homonuclear versus heteronuclear MO diagrams. So homonuclear, everything's going to be at the same energy. Heteronuclear, we're going to have different energies for those. Last thing from 1211 are gases. Make sure you review gas pressure, your named gas laws. So Boyle's, Charles, Gay-Lussac's, and Avogadro's. You should look at your gas variables. So the named laws will have those in there, PV, R, and T. And you can get to any one of your named gas laws using Pivnert, your ideal gas law. Keeping in mind that R is our gas constant that will be given, and T is our temperature, which must be in Kelvin. Anytime you're dealing with a gas, you must have temperature in Kelvin. We also have standard temperature and pressure, STP. When we're talking about standard temperature and pressure, we are talking about 1 atmosphere and 0 degrees Celsius, or 273 Kelvin. So you should know those. It's going to be expected that you know what STP is. You might see something about a fusion or diffusion. Know that if you have a greater molar mass, if you have 2 gases at the same temperature, one has a greater molar mass, it's going to have a slower speed. And gases, their kinetic energy is directly relatable to their temperature. Review Dalton's law. We've used it this semester, so not as big of a deal. You probably remember the partial pressures there. Also, make sure to look over your kinetic molecular theory of gases, which are kind of the tenets of the ideal gas law. Look over your Graham's law. So that's going to actually tell you how effusion is working. And then make sure you review real gases. There's probably going to be a real gas problem on there. You don't need to know your constants, your A and your B, but you should know kind of how A and B work. So both A and B are going to increase with increasing molar mass. And then when we think about our A term is the pressure variable, or not variable, or the pressure constant that's included to account for the differences in pressure. The B term is the volume unit or volume constant to account for the volume of a gas. So with your real gases, you should know that your volume and pressure are affected in this because in real gases, we don't have zero volume for our gas particles. We don't have we do have electrostatic forces between gas particles. Okay. I do have another meeting in just a few minutes, so I'll have to go kind of quickly through the rest of this. The rest of this is 12-12. I've hit a lot of the things as I've gone through, but you should know intermolecular forces for pure substances and solutions, and you should be able to predict if a solution will form. Okay, so make sure you're able to do that. Make sure you know what all of the intermolecular forces are called and how they relate to each other energetically. And you should know your liquid properties. It's the idea of cohesive forces, adhesive forces, viscosity, and surface tension, and how they relate, and capillary action, and how they relate to intermolecular forces. You should be able to draw a heating curve or a cooling curve, or use one of them more likely to analyze a substance. You should also be able to use a phase diagram. You should be able to fill one out, and you should be able to recognize where the triple point is, the supercritical point is, where you have boiling point, the normal boiling point, and the normal melting point. You should understand how vapor pressure and boiling point are related to each other and how they are related to intermolecular forces. In the next chapter where we talk about solids, you don't need to focus too much on the solids chapter. With your solids, know your types of solids. So metallic versus ionic versus molecular versus covalent network. So you should be able to, you should know the properties, and you should be able to determine what substances will form what types of solids. And you should probably know the electron C model for a metallic species. And you should know what your unit cell is. So make sure to kind of review the components of a unit cell and be able to recognize between a face-centered cubic unit cell, a body-centered unit cell, or a primitive unit cell, and then your face-centered cubic, body-centered cubic, and primitive cubic SSPC. So the cells and then the structures themselves, and the idea of interstitial holes for your cations. Okay, I think that's probably the most important things from chapter 12 or whatever we call it. We've already kind of looked at the idea of intermolecular forces within solutions, but some other things with your solutions. You need to understand the solution energetics. So breaking solute-solute interactions, breaking solvent-solvent interactions, forming solute-solvent interactions. You should know what affects solubility for gases. So thinking about Henry's law. And then solid, solute, liquid solvent. So they're very different. So make sure that you know the difference. The type of solute, how temperature and pressure and intermolecular forces are all going to play a role in solubility. We've already talked about the concentrations. Ooh, review your colligative properties. Make sure you know boiling point elevation, freezing point depression, osmotic pressure raising, vapor pressure lowering, those type of things. And you should know the difference between saturated, unsaturated, and supersaturated. Starting to get into stuff that we have done much more recently. So you should be able to solve these as well. So solve and know your colligative properties. You should know a little bit about what a colloid is and the Tyndall effect. The idea that light will reflect off particles. Next we have kinetics. Kinetics. You should be able to solve for general rate laws. So you should be able to solve for your general rate law, integrated rate laws. I believe they give you the integrated rate laws, which is a pretty good indicator that you're going to have integrated rate laws. And then also your relative rates. So make sure you can solve for any one of those. Make sure you can solve for your rate constant and what it means. You need to be able to figure out the units as well. So all of those things are very, very important. You should understand what affects rate. Concentration of something that's in the rate law, temperature, a catalyst, those type of things. You should be able to determine a reaction mechanism. And from a reaction mechanism, come up with an actual rate law or full reaction. So make sure you're able to do that. Understand how catalysis works. And keep in mind, 60% of this exam more than likely will be 12-12. So there'll be a lot on 12-12. Equilibrium spans many, 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 many chapters. A lot of it is the same thing over and over again, but you should be able to solve all types of equilibrium problems. You should be able to solve for your equilibrium constant, big K. You should be able to use K to solve for equilibrium concentrations. You should be able to recognize a heterogeneous equilibrium, and you should be able to write an equilibrium expression. Whether it is Kc, so we have Kc, we have Kp, we have Ka, Kb, KSP, KF, right? We have all of these. Oh, and KW. There's a lot of Ks. If you are given a K, you should know what you're looking for. So if it's like, oh, give me the KC, you should be able to write the KC expression for that. Give me the KP, write the KP expression for that. And those will be slightly different. All of these will be essentially by concentration, but if you're given a Ka, you should know that you're doing a weak acid dissociation. If you're given a KSP, you know you should be doing a solid substance dissociation. So make sure you know what each of these are. Most people are good with Le Chatelier's, but just go ahead, make sure you review it. What else do we need? You should know strong and weak acids and bases. So you should be able to recognize those and understand how to solve for pH for those. You should be able to solve for pH, pOH, pKa, pKb. You should be able to solve for all of those. You should be able to solve for your molar solubility. So lots and lots of things you're going to need to solve for within equilibrium. If there's anything within equilibrium you guys don't remember, please let me know. You need to know the acid-base properties of salts. That's a very common question for people to ask on an ACS exam. You should know the common ion effect. But also how things like acidic or basic ions are going to be affected by pH and the formation of a complex ion. So all of these things you need to think about in terms of KSP and your molar solubility. Oh, I really have to go. You should know how to make a buffer, right? So you can either have a weak acid and its conjugate base, or you can take a weak acid and partially neutralize it, a weak base and partially neutralize it. You should be able to do buffer calculations. You should know how it works, right? So if you have a buffer, it's going to react with any strong acid or strong base that it comes into contact with, neutralize it so it doesn't have a strong effect on that pH. We've already talked about titrations, but you should be able to do all of your calculations with the titration. You should know that amphoteric salts are going to be more soluble in both acid and base. Those type of things. Skip over the next section, which is all the environment that we don't care about. The last part is thermo and electrochem. These are the things we just went over. So I'm not going to really point anything out on this because again, I do have to go. But if there's anything from this section that you guys have any questions about, please let me know. The tests so far have looked pretty good. So I'm not really concerned as much about this part, but definitely check these out. Make sure if there was anything that you don't understand, you either contact me and I'll help you out with it, or yes, the take home is due on Friday. But make sure you do, just because I'm not going over thermo and electrochem does not mean that that is not going to be on the test. It absolutely will. But because of the pretty good grades and the fact that we just went over it, I'm not going to focus a lot on this. But if you guys do have any questions, please let me know. I'm here to help. I'll see you guys tomorrow. Good luck in your exam. Thank you so much, guys. Bye.